So now we are speaking with Kaya Sorli. Kaya is a graduate student at CU. She specializes in modeling and observing of near-Earth objects, or NEOs, things like comets and asteroids. As a member of the Lawrence Livermore National Laboratory's Planetary Defense Team, Kaya has participated in government seminars on global security and understands not only how NEOs could threaten life here on Earth, but also what we could do about it. So thanks for joining us, Kaya.
Yeah, thank you for having me.
We're excited to chat with you. So we figured we'd start with probably the easy, obvious question. What is an NEO?
So an NEO it's an abbreviation because in space and in astronomy, we love those. And it basically stands for near Earth object. And that can fall into two different categories, roughly, asteroids or comets. And for a lot of people, there's not a huge differentiation between those, but asteroids are kind of what most people think of when they think of things that could hit the Earth. If you look at most movies, it's usually an asteroid. It's a big, rocky object, metallic or kind of dust that's all gathered together. And they can range in size from really small, like little tiny, basically pebbles or rocks, and that might be what you see as shooting stars at night, up to things that are almost dwarf planets, like Ceres that are a couple hundred kilometers across. So asteroids, though they are far more numerous, are actually quite possibly not as dangerous as the alternative, which are comets. And comets are really dangerous because even though they're rarer, every single one of them is what we call a dinosaur killer. And that is quite literally a term that's used in the community because every single comet is at least several kilometers across. And a comet can kind of be thought of as like a dirty, dusty snowball. It's a ball, it's a whole thing that's just ice, dust, and it can be different types of ice. But that's also why as a comet gets close enough to the sun, it starts to sublimate and we get that big, beautiful long tail that you're used to seeing in movies and pictures and everything like that. But roughly kind of there's some arguments about things that might fall into both categories that have been starting to emerge over the last couple of years. But for the most part, NEOs kind of fall into those two categories.
Easy enough.
I love the technical astronomy terminology of dinosaur killers. We also have words like spaghettification, which is technical terminology.
Exactly, yeah.
There's the hard time that astronomers can always give to people like biologists to say, well, their most popular word is 10 syllables long, deoxyribonucleic acid. And we refer to things that kill dinosaurs as dinosaur killers.
It gets the point across. It really does. It's the one thing that Hollywood can't make more dramatic than it actually is.
Yeah, right.
Very true.
Well, speaking of Hollywood, we often see in movies and we're literally talking about dinosaur killers. We often talk about these near-Earth objects, NEOs, hitting the Earth, and that's kind of something that we think about because it's one of those things where that could be a very scary and catastrophic event. It sounds like you have done, quite a bit of thinking on this subject and work on, what does this whole situation look like? How can we deal with this? What do we do? So, from your perspective and what you've seen, is the government or space scientists, astronomers concerned at all about asteroids hitting the Earth or comets? And if that's the case, what do we do, in a scenario where that could happen?
Excellent question. So not to freak anyone out, but yes, that is something we're concerned about. I'll say this, it's not a likely event, but it's far more likely than a lot of people realize. That being said, it is quite possibly the only mass extinction event that we might be able to stop, which is quite insane if you really think about it. So when we look at stopping asteroids and comets, if you think about the movies like Deep Impact and Armageddon, they see the object like 14 days in advance, right? If that happens, I'm sorry, we're in deep trouble. But luckily that's not usually the case. So we get hit by stuff every single day. And most of it just burns up in the atmosphere. Occasionally something will make it through. Like if you look at 2013 in Russia, Chelyabinsk, it was hit by an asteroid that was in the order of a couple tens of meters across. And it didn't actually even make it all the way to the ground. It made it through the atmosphere and air bursted. And most of the damage was actually done because people were looking at it up against glass, and then the glass blew out. So the thing is, we won't ever be able to stop all of them. But the nice thing is, especially with asteroids, we actually know where pretty much all of the dinosaur killers are. And every year we learn more. There's entire surveys like Atlas in Hawaii and NEOWISE that are dedicated almost entirely to finding objects that could pose a threat to the Earth now or in the future. So we actually know where a lot of them are. So that's a really good sign, because we actually know that we already know in 2029 an asteroid called Apophis is going to come within the Earth and Moon distance, but it's not going to hit. And so as everything develops, as our knowledge of where asteroids are develops, of how their orbits progress develop, we can actually map out what's a threat and what's not. So that's some of the really good news. Comets, like I was saying beforehand, are a little bit more dangerous, and that's for a couple different reasons. They're really, really big. They move very quickly. We know almost nothing about their interiors. And also, we don't really have much warning time with them often. So I've worked with comets before where we discovered it, and a few months later it crossed the Earth orbital. If you compare that to asteroids, where we kind of know where everything is at least 10 years in advance, anything that could cause real damage, and a comet could really take us by surprise. And so we kind of have to be prepared for that, or at least think of that when we're trying to figure out ways to stop these objects from hitting the Earth. And right now, there's kind of two primary ways that we would go about deflecting these objects. And they fall into the nuclear side and what's called the kinematic impact side. And there's a lot of other really cool ways that people have hypothesized, like laser beams and gravity tractors, which I am more than happy to talk about if anyone wants to go sci-fi. But right now, they're really just theoretical. They're not something that we would actually implement. So if we look at nuclear, we actually literally would take a nuclear device, send it up into space, and detonate. But you don't actually want to blow the object up. Because
so it's not Armageddon. We don't do
not Armageddon.
Okay.
No.
Okay.
Because if you think about it, if you have something like a comet or an asteroid that's a couple kilometers across, you go and you blow it up, and now you have 7 mini comets that are all headed towards Earth on unknown trajectories. Not ideal. So what you actually want to do is go up, if this is the comet, sorry, I probably should describe this as, I probably shouldn't describe this visually. If you have a comet, you actually want to detonate the weapon or the device away from it. And then what you do is the actual blast will cause the surface of the comet or asteroid to shoot off. And that will actually give you a momentum kick. Because if you think about it, as something gets shot off the surface of an asteroid, it's going to push the other direction. And what you're just trying to do is move the orbit enough that it misses the Earth. And that doesn't take a lot if it's a far away object. So nukes are really good for something where it's a little bit closer, actually, where it's a really big object so that you can really just go at it. But let's say that it's something where it's a really delicate material, like a comet, or let's say it's something where we have a long time to go before it's going to hit. As you might imagine, it's not popular to send nukes into space. We have very few international laws as a global community, and one of them is no nukes in space. From the 1967 Outer Space Treaty. So the more popular option is actually something called kinematic impaction. And what that basically is, it's a fancy term for hitting these objects with a battering ram. And that's actually kind of what I specialized in. And it literally means that we would take an impactor and ram it into the object at high speeds. We're talking 10 plus kilometers per second. And you try to move it just enough that it misses Earth. So that's good if the object is small, compact, or if we have a really long time, like 10 plus years, you want to hit it with a kinematic impactor first. Yeah, so those are kind of the two primary ways of doing it. And depending on the object and what we know about it, we would vacillate between those two. But those are kind of the prepared ways that you would go about it.
You mentioned, that both of these kind of require that we know about the object ahead of time. And it sounds like we have a pretty good understanding about where stuff is in space. How does one track one of these near Earth objects? How do we learn about where they are and where they're going?
Yeah. So it once again depends a bit on the object. So if we're talking about asteroids, a lot of how we find them is actually through observing them in like the infrared, or we look for light. Light is kind of how we do everything in astronomy. And it doesn't just mean visible light. It can be infrared or ultraviolet or things like that. And so when we look for these objects, we're actually looking for little blips of light in the sky. So if you actually go to places like the Atlas telescopes or Keck or any of the big ground-based ones, if you take pictures of the sky and then you kind of track with how the Earth is moving, you'll see that most things kind of stay stationary. I mean, the stars and everything do move, but it's pretty slow. So if you're actually looking at images from a telescope and you see something that's streaking across the field of view, you know that thing's a little bit different. And it can be a couple different things. I mean, depending on where you're looking, it could be asteroids, or it could be things like, depending on where you're looking, satellites or things like that, or moons. But with how we look for it, we actually are usually looking for asteroids and comets. So you might look for it by looking to see, is there infrared or things like that in the sky? But you also might just look to see, okay, is there a streak here? And often we discover these for a long time, we discovered these by accident. We aren't necessarily looking for asteroids and comets, but we're like, there's a streak here where everything should be pretty much stationary. What's going on? And when we actually do that, we can track, if we get enough data, first of all, how big the thing is, or how fast it's moving and what its orbit is. So there's a big difference between where the object, let me phrase it this way. There's a big difference between how fast and where things are moving depending on where they are in the solar system. So a lot of what we refer to as these potentially hazardous objects, these NEOs, are actually pretty close into us. They're kind of usually within Mars orbit, but we also have asteroids in the asteroid belt. We have asteroids all throughout the solar system. And then we also have these things called the Kuiper belt and the Oort cloud. And for those who aren't familiar, the Kuiper belt is a ring of icy planetoids and comets and Pluto and other things like that that kind of exist outside the orbit of Neptune. And then there's also the Oort cloud, which is basically a spherical halo of, once again, icy objects that kind of wraps around the entire solar system. And when we are looking at things, where it is will very much determine how fast and where its orbit is. So near-Earth asteroids tend to have pretty stable orbits. They kind of just go around and around and around. But then we also have comets. And comets can be either short period, which basically means they're in the inner solar system. They make their periodic rotations pretty quickly. You can think of Halley's Comet as a prototype of this. We see it every, I think, 80 years. But we also have things called long period comets, which are basically comets that shoot in from way out in the Oort cloud, way out past any planet we have. And then they come in at really high speeds and then shoot back out. And we might not see them again or for a couple thousand years. And those move really, really fast and they're really hard to track. So in those cases, we aren't necessarily looking for a blur on a screen. We're literally looking for light when they get close enough to the sun to sublimate. And so basically for each different type of object, we're looking for them in different ways, if that makes sense.
So really quick, in reference to comets, you've mentioned the word sublimate a couple of times. Could you break that down for us and just, what does that mean when we talk about comets sublimating?
Yeah, very good point. So when we're talking about things that have ice, if you were to look at ice on Earth, we tend to see it either melt, like literally it phase changes from solid to liquid, or you can also have something phase change from solid to gas. So you can have a block of ice literally do what we call sublimation, where it literally changes from a solid ice block into gas, into vapor. And the same thing
the
can
liquid
happen.
phase altogether. It's never liquid between those two phases.
Exactly, yeah. And you can get that if you have the right conditions in terms of temperature and pressure and everything like that. But the same thing can actually happen in space. And in fact, it's easier in space because you're not really going to have ice melt in a vacuum. It's just going to sublimate off. It's going to turn into a vapor and escape. So when you have an object like a comet, that is icy and filled with all of what we call volatiles, which basically means things like water ice, CO2, methane, even sometimes things like cyanide and stuff like that. You can actually have, once it gets close enough to the sun, those ices, those volatiles melt, or not really melt in this case, but basically heat up enough that they turn to vapor. And so when we look at a comet, if you see a picture of a comet that has this big cloud and this tail around it, what you're actually seeing is all of the vapor and all of the dust that's been kicked off as those things turn into gas. And so that actually makes it look much brighter. It makes it much easier to see because the comet itself is much smaller than that cloud, but it leaves this big long tail that can stretch for hundreds or thousands of kilometers.
Let me just ask real quick, because while we're talking about dinosaur killers and gigantic things, what is sort of the line at which something is so big we need to worry about it? And is that anywhere close to like the resolution of what we can see with our telescopes? Is there chances that we're going to miss things that are big enough to hurt us?
So that's, again, good question. When we're talking about things that could cause damage, there's a very big scale, and there's basically a logarithmic, for those who like to think about how things are all related, basically a logarithmic amount of damage that's delivered by how big something is. So up to around 20 meters across, things will usually burn up in the atmosphere or airburst pretty high up. And again, it depends on what we're talking. Like if we're talking this like a solid metal core that came off of a planet when it was destroyed, which is a thing, then that will reach the ground much faster because it's not going to break up as easily. But if instead you have something that's kind of just rubble that gathered together under its own weak gravity, that'll break up pretty quickly. So up to like 15 to 25 meters should break up, not a huge issue. And even above that, it should be so small that unless it literally hits someone on the head, it shouldn't be a huge issue, which once again has been documented. We start to get into problem. What? Say it again?
Oh, is it not often though? It's like
not often. No, that doesn't happen frequently.
Cool.
You have to have some really, really bad luck, unfortunately, for that to happen. Once we get into kind of 50 meters or even 30 plus, depending on the makeup, you start to get some local to regional damage. Once we get into a couple 100 meters, you're talking city or regional destruction. Like if that hits New York, you're in trouble. We really start talking about dinosaur killers, about things that could cause mass extinction events at around 1 kilometer. Because that will leave about a 10-kilometer crater, and it will basically excavate or dig up so much stuff that it will throw it into the atmosphere, and you'll have a combination of maybe tsunamis and kind of blacking out of the atmosphere and huge impact cratering and all of that. Not a fun time. We don't want that. The nice thing is we won't miss something that big. We could kind of theoretically miss some stuff that's in like the 10 to 40 well, not even that, probably 10 to 25 meter range. We do occasionally see stuff like a day or two before it passes Earth, but those things aren't really going to be, they might, if they sneak by us, they won't cause much damage. So anything that's really big, especially on the asteroid side, we will see, and pretty much with asteroids, we'll be able to have time to have a reaction to. With comets, it gets trickier because once again, they could be coming in from crazy places, not just the solar plane. If they're coming in from the Oort cloud, they can come from any direction and at crazy speeds. So the nice thing is we will see it before it comes. We just hope that we see it with enough time to actually react. And for the most part, there will be a reaction, even if it's just a couple months out. You have to, there's a lot of modeling that goes on the nuclear side for that. I don't necessarily have the clearance to know what's happening, but I think you can rest assured that there's a lot that's being done, and we would be able to have some sort of reaction for anything that could cause major harm.
When we think about, potential impactors coming from, other directions than, you said the solar plane, right? Which is like the Frisbee of the solar system, the Frisbee disk, right? But, what about things, that are coming from other directions, like interstellar objects, right? Which are coming from outside the solar system. Is there a lot of thought about that, or is that rare enough that, that's a totally different conversation?
So that's a fun topic because it's something that is so new. For those listeners who might not necessarily be familiar with the concept of interstellar objects, what we mean by that is that there are these comets, asteroids, or other strange objects that can come in from literally other solar systems. So everything I've been talking about up until now are from within the solar system, even if they're from way out in the icy reaches. But if you have something that comes from another solar system, let's say from the Proxima Centauri system near us or things like that, it's going to be coming in at crazy speeds, and it can come in at pretty much any angle. And we actually found it for the first time. We realized it was an interstellar object. The very first one was called Oumuamua. It was observed by astronomers in Hawaii. And they realized something was off because they saw the streak that I was talking about earlier on the images and realized it was moving way too fast to be from the solar system. You can't possibly get going that speed with just the sun as a kind of gravitational factor. So the orbit of that one, it streaked in, we barely got measurements on it, and it shot out, and we'd never seen one before. But then a year or two later, astronomers in, I want to say, the Ukraine found another one. So there's these things come in and they leave and they're never coming back. But at the same time, we're so new to the field of interstellar astronomy that we don't know how many there are. We might have just missed them before now. Or
so this could be like a regular event that we're just now learning about.
It could be, yeah. So at this point, we're not sure if maybe those are the only two we will ever see in our lifetime. But I actually tend to think that that's not the case. I think we're going to find more and more of these. And when we're talking about things in the solar system, everything is very far apart. So though these things move extremely quickly, it's not like it has a high likelihood of hitting the Earth or anything else. It's not, the only reason we see this is because there's a lot of stuff in the solar system. So they definitely could pose a threat. And in that case, we would be in for some trouble. We would have to mobilize a response really quickly, but that's not something that I'm very worried about. They tend not to be too big, and they're also usually, there's not many of them. So I wouldn't worry too much about that.
Well, for now, hopefully we can just watch them and just be amazed that there is interstellar matter coming through our solar system and say, wow, that came from like so far away you can't even imagine.
Yeah, no, it's very, very true. And you never know. Someday our satellites that shoot out of our solar system may eventually be seen as those in other systems. So you never know.
That's a cool idea. I like that.
Yeah.
I like that you just implied life because you said they may be seen in other systems, which is just
yeah, that might be a whole nother question, a whole nother discussion, but it's a fun one, and I don't know, statistically it's unlikely we're alone.
Cool. That I think is an excellent introduction to we're talking about. I want to ask you a little bit about what you do specifically, because you're really big into modeling of asteroids and comets and things. Can you tell us a little bit about kind of what you do and what it's used for?
Yeah, very much. Yeah, totally. So it was mentioned earlier that I worked for the Livermore Planetary Defense Team for a while. So I have finished up with that work, but I'll just touch on it since we're talking about Armageddon sequences right now. I actually was modeling a mission that happened in 2005 called the Deep Impact Mission, where we actually did we rammed part of a spacecraft into Comet Tempel 1. And by modeling that, we can actually learn about the interiors of specifically Comet Tempel 1. And it can help us a lot to understand how impacts happen on space-based objects. Because also, when you're trying to impact something in space, it's an entirely different thing than if you try to do it on Earth. So I was basically trying to model the impact that the spacecraft had when it hit the comet. And we were trying to use the results to not only understand comets, but also apply it to upcoming missions like the DART mission, the Double Asteroid Redirect Test, where we're actually going to take what's called a binary asteroid system, where there's two asteroids orbiting around each other, called Didymos and Didymoon, because that's a fantastic name for an asteroid system. And we're going to hit the small one and try to move it, see if we can change the orbit. It'll be basically the first planetary defense mission. So that was kind of what I was doing at Livermore. And now I'm working for what's known as the Janus mission, which is named after the Roman god of duality, looking forward, looking back. And we're going to be visiting two different binary asteroid systems where there's a small asteroid orbiting around a bigger one. And binary asteroid systems are really, really interesting for a couple reasons. We're trying to figure out why they form, why they split up, what it means for the evolution of asteroids. And what I'm doing is I'm actually modeling the thermal side of these asteroids. So when the spacecraft go by these asteroids, we're going to take visible images, so in the light that we see commonly in day-to-day, and then also in the infrared. And what we're trying to learn from that are things like, first of all, composition and what are these asteroids made of, and we can actually get an idea of that from what we see in the infrared. But we're also trying to learn about how light might have impacted their orbits and their dynamics. And that sounds kind of crazy, like why would light push these rocks around? But when we are looking at, even here on Earth, if you notice at noon, it's not actually the hottest time of day, right? So when light shines down, when solar radiation pressure comes down on the Earth, you actually have light that gets absorbed into the surface or into everything else. And then as you move forward, that light has to get re-radiated out. That's also one of the reasons why it gets hottest in the afternoon, because it takes a while for everything to heat up and then for it to start re-radiating back out before it cools down again. And though that's a tiny little effect, over millions and millions of years, it can actually cause the orbits of asteroids to change. And it can cause things like moving the two asteroids apart from each other or moving them in, depending on how they're orbiting. It can also cause them to start spinning or tumbling in weird ways. And those effects are known as the Yarkovsky effect and the Yorp effect, which basically Yorp stands for Yarkovsky and all the other people whose ideas were kind of combined to form it. And specifically, when we're talking about the case of binary asteroids, it's known as the Bjorp effect. Once again, just great names coming from the astronomy community.
Science.
Yeah, right? So what I'm basically doing is trying to learn how temperature and radiation pressure flux from the sun can impact not only the asteroids as they currently are with their composition and their heat and everything else, but also maybe how they can change their orbits and how it could have led to asteroids spinning really fast, like spinning faster or moving apart or moving together. Because there's evidence that pretty much every near-Earth asteroid exists in a binary multiple times during its lifetime. And that can really affect orbital dynamics. And from a planetary defense point of view, it could also affect what their orbits are and how they could pose a threat to Earth.
So when you're saying that it's, there's probably a lot of reasons why this is really hard or impossible for us to model here on Earth. Like, I can't think of a way that we could actually make an artificial binary asteroid system or something like that.
Anti-gravity room, of course.
Oh, obviously.
Right, yeah.
I should have known.
No, that's actually posed a really big challenge to the planetary defense community and just in general, any space-based impact. You can do experiments here, like we have, you can actually perform scaled impacts and things here, but you always have things like gravity and you don't know if you have the right materials, and there's really no substitute for doing it in space if you can do it. So you're totally right. We can't really recreate it except for with modeling. And even with modeling, we have to test it. So you have to make sure that what you're doing is right, that it actually reflects what's happening in nature. And that's a huge part of science. It's something you have to do in every single field. You have to make a hypothesis, you have to test it, you have to see if it actually compares with what's happening, if it explains what's going on. So in this case, we have models. We have tried to model what impacts look like and what we would do, but we actually really want to do it in space. We want to try it out in space. And so when I talk about things like that DART test, when we're going to impact a mini asteroid, we're going to actually be able to test a lot of what we've been hoping is the solution to stopping things, which is fantastic. I mean, imagine 100 years ago, who would have thought that we could have stopped maybe an asteroid headed for the Earth? So though it's really kind of scary, and I know that a lot of people will probably be a little bit uneasy about some of this, just really the fact that we can do it and we might actually be able to stop it, and I think we have a good shot at doing it, is pretty incredible. It's really a testament to modern astronomy and engineering and everything else that this is a possibility. And we've got a really good chance at saving the world.
That's pretty exciting. That's got to feel good though, like as a scientist, the chance to save the world.
Yeah, very much. Although sometimes I read sci-fi books and there's like a Armageddon sequence. I'm like, oh, so this is what happens if I don't do my job correctly. Good to know.
No pressure. So you've talked a little bit about Janus, and then you mentioned the DART mission, and there's a couple of sort of small bodies missions that are coming up. And we've been asking everybody because, like we've mentioned before, this is a really big and exciting time for planetary scientists. It's at the beginnings of our decadal surveys. We're telling the government what we think is important for the next 10 years. So what sort of small body stuff is going on with these decadal surveys and white papers and things? Are there any like really cool ideas that are coming up? Are they really interesting or really frightening maybe? Or what's going on with that?
Yeah, so just before I even touch on the decadal survey stuff, there's a couple really cool missions that are coming up. So I'm obviously biased towards Janus because I'm working for it. But there's also some really fun ones like the DART mission, and then two called Psyche and Lucy. So my mission, Janus, is actually going to launch with the Psyche mission, which is a larger mission. And it's actually going to visit what we think is a mostly metallic asteroid, which means it was probably the core of a planet that broke up. So I'm personally really excited for that because we've never seen one quite like it. And it'll be a very educational experience, and it'll be a really cool one. So keep a lookout for things like that. The Lucy mission is going to look at Trojan asteroids, which are basically a subset of asteroids that gets caught in Jupiter's gravity and just kind of sits with it as it goes around the sun. So there's a lot of really fun stuff like that. I'm assuming that you've probably talked about the OSIRIS-REx mission and things like that. But there's actually a lot of really interesting work going on with water in small bodies in the outer solar system. So looking at the subsurface of things like Ceres. And if we think back to what I was talking about earlier, Ceres is a dwarf planet in the asteroid belt. And it's kind of right at the line where we used to think it wouldn't have any water, but now we're starting to think that it actually might have ice on the subsurface. And that's something that we're finding out more and more about as we kind of look at the outer solar system. We are finding out that some of the outer solar system moons, and maybe even Pluto, have subsurface oceans, and we're finding out that asteroids by themselves might even have ice on the subsurface, which is kind of crazy. I mean, we used to think that Earth was special because of how much water it has, and now we're actually finding out that we have a lot less water probably than a lot of other places. It's just that it's liquid. So I am I'm still on the planetary defense side, but I'm also kind of now moving into the ice and volatiles and what that means for looking at the outer solar system. We're going to learn a lot from looking at asteroids and what we find in their subsurface, and what we find even with the DART mission. We might see ice underneath, theoretically. It's unlikely, but it's possible. So, and because as we were talking about a little bit with life and stuff, there's basically no greater indication of life that as we currently know it than the existence of water. So I'm personally really excited to look at that. I want to look at the outer solar system more. There's a lot of people pushing for stuff kind of out past Neptune's orbit. And things like moons like Titan, Europa, all of those. But I'm really excited to see if any of the ones for the asteroid belt get selected.
Yeah, that would be really cool. I'm biased too. And, I study cratering in the outer solar system. And guess what makes craters? Asteroids and comets.
Yay!
So we can all work together here on these decadal surveys and white papers. For anybody who is confused by that, white papers are just the sort of reports that we write to turn into the government as part of the decadal survey. So like I'm on one that says, hey, we should really go look at the moons of Uranus. But everybody gets to kind of submit their ideas in a little report. So that's what those white papers are. That's part of our big thing.
And it's a really cool way to kind of source from the scientific community at large. Yeah, so it's definitely something worth looking into if people are interested.
So you mentioned this prospect of, well, we find everywhere we find liquid water, we see life. So,
not everywhere. We're saying that there's more of a possibility.
Well, sorry, yeah, but with the idea that there is, water on, perhaps, on or in asteroids, what are the thoughts about life on asteroids? Is that an idea that we entertain, as you know, as much as we would say, oh well, look at Europa where there might be a subsurface liquid? Is
I
that
wouldn't,
conversation happening?
I mean, I think that it's definitely been brought up. I don't think many people, myself included, believe that there is any sort of life that exists on asteroids or comets currently, or maybe even ever was. That being said, that doesn't mean that they weren't critical in in basically developing life as we know it. So there's a field called astrobiology, which is basically looking at how life and space intermingle and what might have led to the origins of life. And like we were talking about earlier, water is a really critical component for life as we currently understand it. And a big question is, how did water even get here? So the Earth has a lot of liquid water, which is very strange for a couple reasons. First of all, we don't really see liquid water on the surface of many places at all. But also, the Earth is within what's known as the frost line, which basically means that we wouldn't expect ice to have been able to gather on the Earth's surface, or at least not easily. We have liquid water because of the atmosphere, but how did it even get here in the first place? And there's a lot of people in the astro and astrobiology communities that think that it was literally delivered by comets. That comets, these icy snowballs, brought not only water, but all of these organic compounds that might have been necessary for life. Things like carbon dioxide, methane, all this stuff that really forms the building blocks of a lot of who we are and how life formed. So I don't think anyone's expecting to go to a comet or an asteroid in the outer solar system and find aliens, but I think a lot of people agree that they were really instrumental in actually making the conditions for life that we then sprang out of. Because there's a lot of evidence that life pretty much started to exist on the Earth and started to appear almost instantly by geological timescales after the Earth stopped getting bombarded with asteroids and comets, what's known as the late Great Heavy Bombardment. Life started to show up pretty quickly after that. So we think that those really delivered the building blocks and that they were really, really important. And so these small bodies, these asteroids and comets, are basically like taking little snapshots, taking pictures of the universe, of the solar system, as it existed when life and when the planets were forming. So if we look at these comets and what's in them, we can actually get an idea of what were the building blocks that led to life, which is really kind of cool.
So it's a way to kind of look back to the past.
Exactly.
Today.
Yeah.
It's like a time machine, like a type thing.
Exactly. It really is. I mean, it's like how astrophysicists might look at the stars to get an idea, or look far back in time towards the Big Bang to get an idea of
right.
what was the universe like then. We can do the same thing albeit in a shorter time scale, by looking at these frozen bits of time that exist all throughout our solar system.
It's kind of a cool idea, a frozen piece of time that you can look at.
Yeah.
So let me ask you then, we had talked when we were talking with our friend Andrew about Mars, we were mentioning the all the different layers of planetary protection that goes into sending spacecrafts like to other planets. Mm-hmm. Depending on where you're going, you have to go through more decontamination and more steps to make sure you're not bringing external life or what have you to another planet like Mars. So is this something that NASA considers when we're sending objects? Because we're starting to do these missions where spacecraft are landing on asteroids and comets and even bringing samples back and things like that. Is that something that they think about? Is it something that they should be maybe thinking about, or maybe even stepping it up a level?
So that's actually a really important point. Again, it depends on what type of object we're looking at. For rocky, ice-free, just like literally just like dust and rock that's conglomerated under gravity, NASA really, that's the lowest priority on the planetary detection scale, which for understandable reasons, we don't, as far as we know, there's not a lot of reason to really put spacecraft and everything through the ringer to protect something that probably is completely inert anyway. That being said, comets also don't fall very high up on the planetary protection scale, which I don't know. I personally think that we should be a little bit more careful with. But it's also very expensive to do that. And even with our best efforts, we're never going to clean a spaceship completely. A spacecraft will always have some microbes from Earth. But most asteroids are pretty much inert as far as, especially any that we would be landing on in the near future. Like I said, there's the DART OSIRIS-REx missions are pretty much, as far as we know, rock, nothing else. It's just, we're going to visit things not for looking for astrobiology or looking for life. We're looking for how things react when we hit them with battering rams. But
as one does.
Exactly. When we talk about comets, you'd have to be a little bit more careful. And I think that's actually a conversation that's starting to happen. Also, as we look to things like asteroid mining, which will become a thing. It's going to happen. Who knows exactly when? It'll probably be still a few decades, but it's going to happen. We do need to be careful. We not only need to protect where we're visiting, but we also need to make sure that we protect ourselves. So it's something that I think is becoming more and more of a conversation. Of course, they've been doing it since the Apollo era. But as we learn more and more about this, we're starting to realize what our limits are and maybe what we could do more. So it's definitely something for someone like Andrew who's working on Mars. It's a lot more important and a lot more necessary than it would be for even visiting a comet. But that doesn't mean that it's something that we ignore completely.
So what you just said is actually a perfect segue into a kind of a direction that I want to go, which is the idea of asteroid mining. This is kind of, that expression is kind of like a buzzword right now in the like popular astronomy, community. Can you just tell us a little bit about asteroid mining? For you, someone who studies these objects, what comes to mind when you hear those words?
Yeah, so I will very upfront admit that I am no asteroid mining expert, but when you look at these asteroids, there's rock and all this other stuff, but in some of them, you'll see like metals and minerals that don't occur very frequently on Earth. And that can be, even if you just look at ones that are pretty common, like we were talking about these metallic cores of planets that failed. You can have just like solid nickel and iron and all this other stuff that can be hard to find necessarily on Earth, or at least in large forms. And there's other stuff too. You can find, I don't know all the names off the top of my head, but you can find minerals that are very rare on Earth. And there's a lot of challenges that come along with asteroid mining, in addition to the fact that these things are very far away. If you look at even like my mission, we're going to launch in 2022 and we won't get to the asteroids until 2026. So you need to have planet flybys to speed up. It takes a long time to get to these things. And then once you get there, you actually have to find a way. You have to find a way to make sure that this is the asteroid you want, that it's got what you want. Because though we can get an idea from things like spectroscopy and stuff like that of what's in these asteroids, often we have very little idea. We can get shape models from radar, but that's not going to tell you what's inside of it. So you have to be very careful about what you select, because it's really expensive to launch. And then also, even things like just drilling are really, really hard when you don't have gravity and you don't have solid ground. If we're looking at things like a Rebel Pile asteroid, which is one of the ones where everything just loosely gathered with gravity, you might land on it and it might have no way to even hold itself together or to drill. To drill, you actually have to have enough force pushing down on you that you can then push down into the asteroid. So there's a lot of things that are really challenging about that. You got to find the right asteroid. You got to make sure it has what you want. You have to have the tools to actually drill and mine, and then you have to somehow get it back to Earth. And so then the other question is, do you refine it there so it's a lot less mass to transport back to Earth? Or do you bring it back because we have no idea how you would even refine it on an asteroid? And then how do you get it back to the Earth's surface once it's even back to the Earth? So there's a lot of questions. But that being said, there's so many, especially with kind of the increasing demand for these metals and things like that in our society. It will happen eventually, but I think it's going to still be a fair amount of time until we figure out exactly how to do it and do it in a way that's profitable.
Sure.
So this is the thought that literally just occurred to me now, but let's talk physics here. So if we're going out to mine an asteroid, we're actually taking material from this asteroid. We're decreasing its mass, essentially. And eventually it's going to get to a point where this decrease in mass is going to lead to a change in the orbit of the asteroid itself. Because that's how
yeah, it would affect the orbits.
laws work, you know, and Kepler and things. So is that anything that anyone else has even thought of, or is that something that we need to really worry about? Could we accidentally mine an asteroid into hitting the Earth or something like that?
Honestly, that's a really good question. If I had to guess, well, I mean, there definitely is actually a lot of worry when we look at places like potentially corporate companies that aren't beholden to taxpayers and safety codes and everything, going out to mine asteroids or to do other things to asteroids even. You do have to think about what they're going to do in terms of affecting orbits and stuff like that. Even if we're not mining, even if we're just going out to visit things, you do have to be careful. It would be something like that is going to probably have it's going to take a while for the orbital effects to make it hit Earth. Because it wouldn't be like, it's not like you're going to like kick it towards Earth or anything. It would still be a slow progressive process, but it doesn't mean that we wouldn't want to be careful that in the future we don't put it on a trajectory with Earth. So it's definitely something to keep in mind. It's something a lot of people have thought of. Like, what do you do when potentially space is entirely globalized and it's not necessarily even just the space agencies going around? Because right now we have a limited number of players in space, and for better or worse, that there's a lot of people who would argue that that'd be actually better if we had more players in space. That's a whole different issue. But that's actually something that there's a lot of concern about. I mean, even just look at the Earth. We already have a lot of space junk up there. The more players you get, the more stuff you're going to have, the more effects you're going to have, and the more chaos and entropy that you'll also have. So it is definitely something that you'd want to keep in mind, and you'd actually probably want to eventually, theoretically, we're going to have to institute space law. That is a whole nother, but we haven't even figured out like Earth globalized law. But that's something that we will have to think about. That's a really good point.
This reminds me of this conversation that we were having with Dave Brain a couple of weeks ago, talking about Mars. And I asked him the question, I was like, what happens when we say in the future, we've done enough Mars missions and there's enough stuff going on Mars that we are no longer thinking about the scientific goals. We're, kind of proceeding normally. And his response was, in other words, what happens when we are living on Mars? And so it kind of makes me think like, at some point we'll get to the point where it's no longer these scientific objectives. We are just living in space. We're, interacting with the rest of the solar system in like a totally nonchalant way. That's not, these crazy things.
It's mind-boggling to think about now, but you're entirely right. It's something that will eventually happen, and it will be, it's very much a thing. And so everything starts off sciencey because it takes so much capital and so much energy to actually start these things. That usually stuff like this starts off spearheaded by places like NASA or other, or ESA or JAXA or other. I'm naming different national space agencies for people who might not be familiar with all of the acronyms that we use. But yeah, eventually you get players like, we already see people like SpaceX and Virgin Galactic and like all of these. There's a ton of them now already, and you already see a lot of space startups that even you might not know the name of, but that are already looking at stuff like this.
Right.
The purpose of science there's a lot of purposes of science, but one of the purposes of science is just to ask questions and to pursue things that don't necessarily make sense at the current time. You try to push the boundaries and you try to learn more, and then you see what you get back and you try it again. And eventually you hope that makes its way into everyday life. It's really strange for us to conceptualize that with space, because it is something that exists so far at the edge of possibility. It inherently pushes the definitions of what we understand as possible or reasonable. And it's strange to be like, oh yeah, eventually we will live out there, but it almost certainly will happen, assuming an asteroid doesn't get to us first.
Well, and that's great motivation. Well, motivation might be the wrong word, but the idea of, of surviving these kind of catastrophic events. We talk about asteroid impact, or in 5 billion years, the sun will expand and, kind of swallow the inner solar system. And so, these conversations are kind of interesting to think, well, if humans are to outlive these events that would otherwise, completely erase us, then it's mandatory that we figure out, how to interact with space more readily. And so it's not so difficult and expensive and all that. So yeah. It's interesting. All right.
I think that is a beautiful way to kind of wrap up the official conversation part. That was a wonderful, grand summary of science. I like it.
The existence of humanity and how we survive.
Right. But we are not done yet, because we are going to do our new favorite thing that we're doing. We're calling it Capcom Q&A, where we have questions submitted by the public, and we're going to quiz you on a couple of things that people from our audience want to know.
All right.
I'll let Colin kick off the first one there.
Oh, right. So we kind of talked about this, but I guess this could be a good summary too of the episode. So this first question that we have, the question is, how big of an asteroid would destroy life on Earth?
All right. Well, so destroy life entirely is a different ballgame, because as we know, the dinosaurs didn't make it, but mammals did, luckily enough for us.
Okay. Okay, so yeah, let's ask that question. How big would an asteroid have to be, or any impactor, to make Earth no longer a habitable planet?
I think it's hard to make Earth completely uninhabitable, because there are some microbes that'll probably make it through, but you'd pretty much have to start from scratch. A couple thousand years later, at least a couple thousand years later, because if you have a big enough impact, you not only, a lot of people get worried about the actual crater, but that's not really the issue here. It'll take out a lot of people, don't get me wrong, but the issue is not necessarily the crater. The issue are the tsunamis that you'll have, and the dust blocking out the atmosphere. And if it's big enough, it will literally cause the atmosphere to incinerate, and you'll have global temperatures that go crazy high that basically burn everything up. There'll be noxious fumes everywhere. It's not going to be a fun place to be. All the glaciers will melt.
Bad news.
For that, I mean, to actually have that happen, you're talking a couple kilometers. Like one will start to do it. Once you're into kind of 2+, you'll have some large effects. You'll have mass extinctions at that size. I don't know the exact number for total global inhabitability, but I would probably guess it starts to happen around 10 kilometers. I could be wrong on that, but once you get kind of 1 to 5 and up, you're talking mass extinctions and some very, very bad effects. And basically it will be like Earth is starting over for the most part, but it's life has a way of sticking around when it's kind of impressive.
I don't know if this is right. I guess Kaya or Tara or John, I've heard somewhere that life has independently started. We think that life has independently started 5 times on Earth. Is that right? That I don't know if it was time-based or space-based, that in different locations or what. Have any of you heard anything about that? I
don't think there's any confirmation that is true.
Okay.
I'd probably side with what Tara's saying.
From rock records and things, we do have records of several mass extinctions. That's actually a thing that happens really regularly on Earth, surprisingly regularly.
Mm-hmm.
But I don't think we have any proof or really any solid evidence that life has completely wiped out and then restarted.
Okay.
We do have evidence that life has evolved or thrived in very strange circumstances.
Okay.
Like if you actually, something that has big impacts for potential oceans, subsurface oceans on the moons in the outer solar system, is the fact that we actually have organisms that have thrived with access to no sun, living entirely underwater, under ice caps. So, but I don't think, I don't necessarily know that there's any sort of confirmation that we've seen life evolve independently.
Got it.
So our next question is one that I get all the time. What is the difference between an asteroid, a meteor, and a meteorite?
Size. Almost entirely. All meteors and meteorites are, they're all in the asteroid family. But a meteorite is basically something that hits so a meteor, everything's an asteroid. Everything's a space rock for all intents and purposes. But a meteor is basically something that hits the atmosphere, and you might see it as a shooting star, and a meteorite is something that makes it all the way to the bottom. So if you ever seen like pieces, if someone's ever passed around a piece of meteorite, that means that it actually made it all the way to the Earth. A meteor mostly just blows up in transit, so that's something where you might get a big air burst or something like that, but there's not necessarily like shrapnel on the ground. An asteroid they're all asteroids until they hit an atmosphere, basically. And then usually, I say size because we tend to call these things like shooting stars and things like that. You wouldn't really call one that was really, really big a shooting star. You'd probably still call it an asteroid, but you're just it basically just depends on if it makes it to an atmosphere and if it makes it to the ground.
So on the subject of things hitting the ground, another one of the questions that we got is, have we as humans ever observed an asteroid hit a planet? And that's what the question is. Have we seen an asteroid hit a planet? I'll interpret that as maybe, have we seen an asteroid hit another planet that's not Earth? Do we see?
Well, we've seen them hit here.
Yeah, right.
Yeah. No, but we actually have, yeah. In fact, we've actually also seen a comet hit another planet. So I want to say it was the 90s, a comet, I think, was that Shoemaker-Levy? With funny names, hit Jupiter, and it was really, really cool. If you're listening and haven't seen pictures, I would definitely recommend looking up that event because it's really, really fascinating. So we actually got to see comet hit a gas giant, which was potentially the coolest scenario. But we have also seen little things hit kind of all over the solar system, or alternatively, we've also seen fresh craters, even if we didn't necessarily see the impact. Because often you can see on these planets how new a crater is depending on the color. It'll be redder or lighter or something like that. So we have seen things hit. We actually have another member of our group who observes small little flashes on the moon even. So we have seen that. I don't think we've seen a really large one, at least not during the period of modern observing. Terry, you can correct me if I'm wrong on that, if you know. But I don't think we have. I think the comet impact on Jupiter was pretty much the climactic event in terms of impacts.
Yeah, that was a big deal. I think if something really big like that happened, we probably would have heard about it by now. All right, and our last question from the public here is a pretty simple one, I think. How are asteroids made? Where do asteroids come from?
Great question. Something we're actually still working on, but the general belief is that when the solar system was starting out, it kind of started as a giant cloud of dust and gas, and of course at the center we have the sun growing and eventually igniting and turning into the sun as we know it now. But you have all this other dust and everything out in the solar system, and if you have a little bit of gravitational perturbation, that dust can start to collapse and at the beginning you might get little tiny pebbles or just barely there dust collections. But because of gravity, those things start to collide. They start to come together. And that results in larger and larger pieces that eventually kind of collide and grow. And what we call these are basically rubble pile asteroids, because it's literally like you're taking dust rubble and it's combining, it's coalescing under its own gravity. And when we look at the kind of solar system as it exists now, we can actually still see these. So there's lots of different, we've visited some of them or are going to visit. There's lots of asteroids that are just the product of rubble piles that get bigger and bigger and bigger and bigger. And theoretically, if it can get big enough that it can attract enough to actually cause if an asteroid can attract enough stuff that there's enough pressure at its center to start to heat up and basically start liquefying, then you can start to get metallic or planetary cores. So if you actually look out in the asteroid belt, there's pieces from either failed planets, what we called failed planetoids, or from things that were scooped off. Like there was a giant impact on Vespa, which is another dwarf or large asteroid dwarf planet sort of thing in the asteroid belt. And we can find pieces of Vespa scattered throughout the asteroid belt that tend to be more metallic because there was enough pressure that they actually turned metallic. So asteroids can kind of broadly be categorized into rubble pile, where it was just everything gathering under gravity. It's a very weak, but they can get pretty large asteroid. Or if it gets hot and dense enough that it actually turns metallic, then you can literally get hunks of metal flying through space.
Well, we have one of those on display in the lobby of the Fiske Planetarium. So whenever that opens back up again, come check it out. It's free. You just walk in. And this is for anyone listening who's like, oh yeah, you can just walk in and touch one of these huge pieces of metal. I think the one that we have is largely nickel. Is that right, Tara?
Iron and nickel, yeah.
Iron and nickel. It weighs like 150 pounds. It's this massive thing that I think we are borrowing from the Denver Museum of Nature and Science.
It's a little chunk. It's not even a whole meteorite. It's just a chunk of the one that created the meteor crater in Arizona, which was, I think, a couple of tens or hundreds of meters across. It was pretty big. The crater itself, a kilometer.
The meteor crater is about 1 kilometer across, which means it should have been about 100 kilometers, 100 meters across. Sorry.
Yeah, so we just have a little chunk of it, but yeah, it's maybe 3 feet around and weighs like 120 pounds or something. It's cool. So
cool. Well, that wraps up our questions from the public for you, Kaya. So thanks for summing, that was a nice like summary almost of the episode of this whole conversation that we've had. I wonder if there's anything else. Is there anything, Kaya, that you would like that was on your mind that you were like, ooh, this would be a really cool thing to bring up, but we didn't get to it today?
I think we covered a lot of it. I think the one thing I would reiterate is don't be afraid that this is going to happen. We actually have measures in place. But that being said, we might be able to stop it, which is potentially the most crazy thing humanity has ever been able to do. That we can stop another small, almost planet thing from hitting ours, and that we can maybe save ourselves from what space can, of something that space can throw at us. It's really pretty incredible, and it's a real testament to a lot of hard work from a lot of people, and it's something that's only going to grow as we continue. We're going to learn where more asteroids and comets are. We're going to learn more about this solar system that both shelters and threatens us. And for anyone who wants to study stuff like this, it exists. I didn't even know there was a planetary defense team until I joined it. But it totally, it's a thing that's very important, and we're going to keep finding new ways to find solutions to the things that space can throw at us. And we're going to need more people. So if you have any interest in it, take a physics class, take a math class, go to Fiske, learn about space. You won't regret it.
That reminds me, I don't know how this slipped through our fingers, but something that we always like to ask, and we can do this briefly because I know we're kind of past our official ending time of 11, but how did you get to where you are? When you were growing up, did you say, I want to become a planetary defense scientist to your parents, or did that, evolve and it became something that you just kind of fell into? What's your kind of, your story of how you ended up where you are?
Yeah. So actually, fun fact, I was terrified of an asteroid hitting the Earth when I was little. I don't know why, but I was. So I guess the whole face your fears mantra really comes true. But I actually grew up on out in rural Montana, out in like ranch country. And so like a lot of people, I grew up and the Milky Way was just a ribbon across the sky every night. It was vibrant, and I would sneak out of my house at night and go out in the field and stare at the stars. And ever since I've been little, nothing has enthralled and inspired or terrified me as much as space. And if that's not something we're studying, I don't know what is. But I'd always loved space. I'd always kind of fallen in, it's something that had totally enthralled me for so much of my life. I remember I got to visit the observatory on Mauna Kea. And I was like, wait, you can study this? Like, you can study space for a living? And that was when I was in elementary school. And so as I got older, I started taking physics and math, realized I really liked it. At my undergrad at Duke University and also UNC Chapel Hill, I studied physics and comp sci. That's actually another thing. If anyone is interested in going into space, take comp sci classes. It will make your life much better in the long run, and you will be very happy you did. And astronomy, I actually started doing galaxy observations there. And though I liked it, I realized that my heart kind of was more within the stuff a little closer to home. I liked planets. I liked space rocks. So I actually ended up looking at ways to do space research and applied to Lawrence Livermore. And actually they said, so we have this position. It's on the Planetary defense team. And I was like, come again? And I ended up working with them, and it was an incredible experience. And so I realized I really liked small bodies. I liked planets. And that's kind of how I ended up at CU, because there's a huge amount of planetary research here. And it's really a fantastic time to be in the field, because there's so much that's going on and so much that's about to happen with the return to manned missions, with all of these missions that are going to asteroids, comets, everything else. It's kind of like being a kid in a candy store. You just got so many great things happening. So it kind of started off as just that pure, unadulterated love of space and the wonder it inspires that so many people have. And I guess I was lucky, but I found ways to make it happen. And so it's totally a thing that can happen. I didn't even know planetary defense was a real thing. I thought it was just in movies. But no, it actually is it's a very real thing. And there's going to be a whole lot of those that kind of start to pop up in the next couple decades. Like we were talking about asteroid mining and living on other planets. And we're going to start seeing the groundwork laid for it. It already has been, but we're going to keep seeing the groundwork laid for it. So it's a good time to be in space, especially if it's something that inspires you.
Well, awesome. Kaya, thanks so much for, getting on here and chatting with us about asteroids and planetary defense. It was really cool to hear your story and your perspectives on a lot of these things. So we really appreciate your time.
Yeah, thank you so much for having me.